Okay, let's get started. So today we're gonna start talking about the alternating direction method multiply, or sometimes called the method of moments. Okay, in short, it's called ADMM. So we're gonna go to this algorithm. Today we're going to do quite a bit Blackboard writing today. So if you need to take a note. Okay, so some of this is not going to be on the slides. So the slides just provide you the basic study, but for today's class you definitely need you want to take some notes. So what I'm going to do is going to briefly introduce this ADMM. Also talk about why we want to do that. Then we're going to dive into some details. The goal for the ADMM, okay, is we want to, as we talked before, if we have this large data, if we want to run a simple logistic regression to the data, then what we want to do is we can have in the algorithm ready, right? And then sort of go through the iterative algorithm for the logistic regression, and then we figure out using the parallelization for each step of the algorithm, right? For each iteration, we apply this is a large data computation. So therefore, we can like MapReduce at each iteration. So then we can achieve that. Now the question, people think that's still pretty time consuming, and also it's have a lot of the I/O into the system. Now the goal for the ADMM is people try to ask the question is can we divide the data first? Okay, we have very large data. Can we divide it into small partition first, and then we can just for each process we can just work on each partition or each subset of data individually. Okay, and then at the same time we also have a central to control the process. Somehow, okay, we can making this local optimization, which is a small job, and then you using some algorithm to merge them together to achieve so-called global maximization or global optimization. So this is the goal for the ADMM. The goal ADM, of course, since I introduced it, so this is the process is durable, and it's mainly through this is the algorithm ADMM. So the goal here is we want to introduce robust method for arbitrary scale optimization. All right, so the machine learning and the statistics with huge data set, and it also has dynamic optimization on large scale network. This has so-called decentralized optimization. Okay, we're using devices, process agents, coordinated to solve large problem by passing relatively small messages. So the whole idea is also it can be seen is a so-called a parallelized optimization. Okay, so your optimization job right now you're doing now is you have everything data loaded into the memory, and you run the optimization in the memory, but then the ADMM, the goal we try to solve is sort of like so-called decentralized optimization or parallel optimization. Is how we can perform this optimization in the in parallel, okay, by using multiple computing clone nodes together. So I'll state the slides. So this slide and the next slides, these two slides are pretty simple in here, but I'm going to spend I think I'm going to spend quite a bit of time explaining why this happens. Okay, so that's why I'm doing the Blackboard writing is to explain to you what happened. This is like why this step is valid. Okay, so that's because I don't want to just give you guys an algorithm. Guys, what I want to do is really understand what's going on behind the algorithm. So this thing mainly is built on to this is a Lagrangian dual problem. Okay, so how many of you are familiar with the Lagrangian dual problem, or have you heard of this before? Okay, so then this is okay. If you haven't heard, it's okay because that's why I need to explain it. But the Lagrangian problem you guys are very familiar with, right? So we're gonna mainly focus on this is one particular problem, which is optimization minimization with equality constraint. Okay, so this is the equality constraint. This is particularly the linear equality constraint. You're gonna see why we just focus on this because this is a for our problem. This is the cases we're gonna focus on. So let's assume your fx is convex. Okay, it's a convex function. You have this convex equality constraint optimization problem is we have minimize fx subject to ex equal to b. This is equality constraint, right? This is the simple. This is I spent like one class just talk about the optimization, so you guys should be familiar with this. Now the Lagrangian, okay, Lagrangian, it can be Lxy. Y here is Lagrangian multiplier. I use like a mu before, but now I'm just using y. Okay, this is it's kind of sloppily on notation because y in our like the data analysis we typically refer to the to response variable, but here just by context you should know. In here, y refer to the Lagrangian multiplier. Okay, so Lagrangian is going to be fx plus y transpose ax minus b. So this is this is a linear system, right? So this is we have like a p equations. Okay, so this is a vector. Now the dual problem. Okay, the dual function for this is for this Lagrangian problem is called gy equal to infimum of Lxy respect to x. Now this is a dual function. Dual problem is we can maximize this is gy function. Okay, maximize this dual function, which is a dual problem, is equivalent to the original Lagrangian problem. All right. So here is actually there. Let me just let me just state the results in the slides, and like I said, I will go through the details. The what we can do is we can if we can solve this dual problem. Okay, dual problem is by maximize this dual function. Remember what is our Lagrangian problem? Our Lagrangian problem is try to minimize this is fx subject to this is ax equal to b, and then we convert it to a Lagrangian function. We want to minimize the Lagrangian function, right? So minimize the Lagrangian function, which is minimize this Lxy. This is optimization problem is equivalent to this is a dual problem. Okay, dual problem basically is maximize this gy. What is gy? Gy is basically minimize the Lxy, the Lagrangian function with respect to x. So the dual problem is a max-mili problem. Okay, is a max-mili problem. The original Lagrangian problem I will show you in 1 second is actually the min-max problem. Okay, so we can maximize this Lagrangian with respect to y first, and then we minimize that with respect to x. So it's a min-max problem. Now I'm seeing here is this is a Lagrangian problem has the equivalent dual problem, which is a max-mili problem. And if this is true, okay, if this is true, we can then see this is because why I want to do that? Because for sometimes your dual problem is actually easier to work with. Okay, this is you're gonna particularly gonna see it in the SVM, in the support vacuum machine. You're gonna see that we can actually its dual problem is much easier to the primer problem. So this is called a primer problem. Now, say suppose we can solve this dual problem. Okay, we're given an x. Then we can maximize this gy. So then we can recover the optimal value for the x by minimize this Lxy star. Okay, y star is already saying we already have an optimal point for the y. Then we can just minimize x by plugging in the y star into the Lagrangian function, and then we can minimize this whole thing, get an x star. Then this is x star is our the target. Okay, it's our like minimum value for x. And then this thing can basically solve x star and y star iteratively. And this iterative process is called the dual ascent. Okay, dual ascent. But dual ascent is we try to use a gradient method for dual problem. We update our y by by using this by plus some gradient, okay? Because we want to maximize y, right? So if you want to maximize y, what we're going to do is we want to move the y in the direction of its gradient, right? In the direction of its gradient. So therefore, the y in the next step is going to be equal to the y in the previous step plus some step size multiply the gradient of this g function of yk, right? The gradient. So the gradient of this gyk is actually equal to ax minus b, because remember is the gradient is respect to the Lagrangian function, and then if we take in the gradient of Lagrangian function respect to the y, which is Lagrangian multiplier, is ax minus b, right? So therefore we can update this as y in this way. By doing this, then we can have a so-called dual ascent method. Okay, this dual ascent method is basically saying we can also, if you want to minimize this Lagrangian function, we can go through this iterative step. In each step, what we're going to do is for the x k plus 1 for the next for the x in the next step, we plug in yk into Lagrangian function. Okay, then we minimize our Lagrangian function respect to x, because y is known, so then the function only x is unknown, right? So you minimize that function, you get in this is xk plus 1. Then we update. Okay, then we're gonna do the maximization on the dual problem. We're gonna maximize this is g of y. Okay, maximize g of y. So maximum g of y, what it does is basically we can plug in xk plus 1 into a Lagrangian function. Okay, right? Because we want to minimize this Lagrangian, we know xk plus 1 is minimize this function. So we plug in xk plus 1 into this Lagrangian function. Then you can see the first term k plus 1 is actually a constant, right? Doesn't contain any y. So if you take a gradient, this first term goes away. Second term is going to be basically it's going to be a xk plus 1 minus b. This is a gradient respect to y, right? So therefore, what we're going to update it is we're going to do the updated y in the direction of its gradient. All right. Then this is a dual update. So therefore, you can starting from somewhere. You have x0, y0 starting some point. Then you update your getting your x1 based on y0. Then you update y1 based on x1, and go on. Okay. So this problem then it can be seen is a dual so-called dual ascent for the Lagrangian the maximization or minimization. This is I want to see one thing. Okay, the problem here. Okay, if you want to update your y, basically you want to update your gy, right? So what is gy? The gy in this case, remember gy here is basically given xk plus 1, right? We know x in next step. So this is going to be f xk plus 1 plus y a xk plus 1 minus b. Okay. Right. So this is your g y given you have in xk plus 1. So this is your target function. So therefore, your y you want to maximize. Okay, you want to maximize this function with given y. And now if you look at this function, if you maximize this function, what is the maximum should be? Y can be anything. Right. So what is this is a function? What is the maximum value of this function? Huh? It's infinity, right? So it's exactly infinity, because as long as ax t plus 1 minus b, this does not equal to 0, right? So your y can be either infinity or negative infinity, right? So this thing is actually, if you just maximize this function, you actually cannot you cannot having a specific function y. This is because the constraint ax minus b equal to 0 hasn't kicked in yet. Okay, if that kicked in, then this is not this is not gonna be the infinity. Now this is the reason. Okay, this is the reason why. This is the reason why when we do the second maximization, instead of directly, this is y value, instead of directly maximize this is gy function, what do we do is we use the gradient method. Okay, this is because if you directly maximize this function, y actually go to infinity, you don't have any solution. Okay, so but we know in here we know this is we don't want to this is y to infinity. So therefore, what we're going to do is we're going to move this y in the direct direction is gradient to make this is the Lagrangian value to increase a little bit. Okay, to be going to that direction, but instead of having the maximum. So that's this is I want to say here. This is why we're doing this is doing the second step by adding here. This step here is basically is try to solve the maximize this is a dual function. Okay, maximize dual function, but it's not a sort of like a real maximization. What it does is we try to just increase its in direction, because as this algorithm go when the x gradually converge to the optimum point, you're going to have in the ax minus b actually close to 0. Okay, so it's going to be gradually close to 0. So therefore, this step is eventually going to goes away. But at the early steps, okay, at the early steps, this ax minus b is not 0. So therefore, if you just directly maximize it, then you got to have y is just infinity, which is going to the whole algorithm is going to break down. Okay. Okay, so this is sort of like the framework. Okay. Now what I'm going to do next is I'm going to fill in the details, because now what you see here is this is what I tell you, right? So the Lagrangian is equivalent to this dual problem, but y is equivalent to dual problem, right? So this is like a details. It's still unclear. So so what I'm going to do next is let's fill in this gap. In this way, you can understand this is a sort of like dual problem a little better. Now, let's go back to the blackboard. So our original problem, okay? Original problem, we want to minimize fx, okay, with respect to x, subject to this is constraint ax minus b, right? So equal to 0. This is subject to this is a equality constraint. Now our Lagrangian function, okay? Lagrangian function Lxy. So we want to minimize this is a Lagrangian function x with respect to xy is equal to fx plus y transpose ax minus b. Okay. Now this is a Lagrangian function, okay? This is a Lagrangian function. I would say this problem is equivalent to a minimax problem. Is minimize x, maximize y of Lxy. I will say this is a minimax problem. Okay. What this is a minimax problem is in the problem above, we maximize xy simultaneously. Okay, we max at the same time. In the problem below is a two-step maximization. Okay, you maximize this is Lxy with respect to y first. Okay, so then then this function become a function of x, right? So you maximize respect to y first, then this is inside here is become a function of x, and then we can minimize this thing with respect to x again. So this is actually the two-step is a minimax problem. Okay. Now can anybody tell me like why these two equivalent? Does anybody have an idea like why these two steps are equivalent to each other? So in order to see that, okay, in order to see that, you can let's just look at the second this is the second part, the little bit inner maximization first, right? So maximize y of Lxy. Let's break this is so let's break down. So this is Lxy is equal to this guy, right? Now you want to maximize this is with respect to y. So what is the maximization for this problem? This maximization problem, basically, this maximization is if ax minus b equal to 0, right? If ax minus b equal to 0, then the maximization is fx, okay? Because then it doesn't matter what y is, then this term is 0, right? Now, if ax minus b is not 0, what is maximization is going to be? It's going to be infinity, right? It's going to be infinity. Now, this is a function. This is a function we try to minimize, okay? Because this is maximization of this guy, right? Now, if we want to minimize this function with respect to x, what's the problem? What is the problem? The equivalent problem is going to be. Because this is if ax does not equal to 0, then you want to minimize this function. It's going to be what? It's still going to be infinity, right? It's still going to be infinity. So therefore, if you want to minimize this function, it has to be constrained to the first condition, right? To the first scenario. So therefore, minimize this function is equivalent to minimize fx subject to this constraint, right? So therefore, this problem are equivalent, okay? Because everybody follow me? Because this is a function is fx is maximize Lxy with respect to y. This is what we got. We have two scenarios. Now, if you want to minimize, okay, if you want to minimize this thing, if you want to minimize this thing with respect to x, so x cannot be in this set. Ax minus b cannot be like not equal to 0, right? Because if it doesn't equal to 0, then no matter what x you choose, your minimization is infinity, right? It's infinity. Therefore, then if you want to minimize this function, then ax minus b has to be equal to 0. Okay? When ax minus b equal to 0, then minimize this is a Lagrangian is equal to minimize fx. Right? So therefore, it is back to the original problem, which is this problem. Okay. So therefore, this basically shows you minimize fx. You have minimize the Lagrange function, which is equivalent to this minimax problem. Okay. This is now I want to make another statement. Okay. Even bolder like a statement. I'm saying minimax this problem. I can switch the order. Okay, I can switch the order. I can maximize. I can minimize x first, and then maximize over y. I say these two are equivalent as well. Okay, I'm making another statement. I say this minimax problem is equivalent to this max mini problem. Okay, is this the obvious statement? And I just switch this to, or I do this, can I just switch this to still make the problem equivalent to each other? This is actually not that obvious. Okay, this is actually not that obvious because there's actually a theorem which is saying if you have a function of this is a fx at y, this is actually equal to the infimum of X. Okay, this is sup stand for supremum. This is infimum, right? So this is basically if you compute, this is the max, this is maximization, this is minimization, right? So this is the max mini, and this is the mini max. Maybe I just because this is writing this way is more rigorous, but let me just we are not gonna go through the very strict no, we can just because I will just mainly the main is I want to convey the idea to you guys. Okay, so this is let's not be that rigorous for now. This is actually this is a general. So see, fx is some continuous function, right? So you want to minimize. So the max mini. If you minimize x first, then maximize it. Okay, this value should be always less than or equal to this minimax power. Okay, so is actually there. If you with that in mind, okay, then these two equivalents actually is not that obvious, because what you're gonna see is this value in the above is gonna be always less equal to this guy. Okay, they're only at one point they're gonna equivalent to each other. Okay, they're gonna equal to each other, and that one point is so-called duality gap. This is duality gap equal to 0, which is going to make them equivalent. Okay, so we can just I'll show you just in a second, like not the rigorous proof, but it's more like geographically why this is true. Okay, now why this is true. So I'll give you like a very hand-waving heuristic proof. Okay, so you can basically see why this is true. If we let my equal to if we let my equal to the minimum x of fxy. Okay. Now, if we so basically is this one, okay? It's got this that's equal to my. So let's see, making this is a bigger mx. Okay, this is small. This is small mx. This small means minimal. Okay, small means minimal. Bigger, this means maximum. Okay, this is equal to maximum of y with respect to fxy. Okay, so let's making this notation. Okay, now by the definition, should be like infimum and supremum, right? So now I'm just using min-max. Essentially, is they are most of the cases they are you can treat them as the same. Okay, but in here we can say there's always exist two values x hat and y hat, such that such that we can always find this is a two x and y hat, such that this is a such that this is this guy right here. So it is a sup of this. So m x hat is going to be less than or equal to infimum of fx plus 6. Okay. On this side we can also say sup of sup, which is it's a minimal. Okay. So in here it's going to be maximum of this is a small y minus its own. It should be less than or equal to my hat. So what does this mean? This means because my is the minimum of this thing, right? Now, if you maximize, okay, if you maximize this my, Okay, if you maximize this value, if you minus some epsilon, you can always find some y hat, which is going to be bigger than this is the maximum value minus some epsilon. Okay, you can always find that point, right? Because if you can, then this point is going to be maximum, which it cannot be, right? Because we know maximum is this guy, right? Everybody follow this argument? Because if you this is your my function, okay? You maximize this is the maximum of this my function, small my, okay? You maximum this function. So if maximum value, you subtract some epsilon, some small value. You can always find another y hat, which is in this function can be bigger than this is the maximum minus small epsilon, right? If you cannot find any y hat is bigger than this value, then this value should be maximum, which is contradict to this side, right? You can see so this is true. Same argument to here as well, right? You can always find the minimization. So this is the minimum of bigger capital MX. If for this minimum you add some epsilon, you can always find some x hat is less than this guy, right? If you cannot find x hat is less than this value, then this is the minimum, right? Which is contrary to this is the minimum x contrary to this guy, right? So therefore, you can always find x hat and y hat such that these two equality always hold, right? You can hold that equality. So therefore, with that in mind, then we can say basically is so this guy is less than, then we can basically just connect the dots, okay? So we have this maximize this my minus epsilon less than equal to my hat. Now this my hat, I just need to fill in some between. This is less than equal to f x hat y hat. Okay. So then this mx is the minimum of this thing, right? It's minimum of this thing. So therefore, if you plug in any x hat into there, it should be bigger than or equal to this minimum. Right? So then this value is also less than or equal to this mx, because this mx is the maximum of this function. So therefore, if you plug in any x hat into there, the y hat into there, this also make the whole. Right? So therefore, if you're connecting this thing together, we can basically say if you let this is the maximum of small f y minus epsilon, basically is less than or equal to minimum of this. Okay. If you let epsilon goes to 0, then what you see here is basically this is the max mini is less than or equal to minimax. Okay. So that's this is sort of like the okay. Let me just. So therefore, what do we have here? Maximum of minimum of this my minus epsilon is less than or equal to minimum of capital X minus epsilon. Okay. So if we let epsilon goes to 0, then we have this maximum of small my less than or equal to minimum of the max the fy. Right, so therefore, we have the original the claim. This is results also you can actually think this is this actually make intuitive sense, right? This actually make intuitive sense. So what it basically saying is, if you have a function, you try to maximize it first, okay? You try to maximize first, and then once you have that maximization, okay, then you take a minimum on that maximization. Then that basically the lower bound is so the minimization is the minimization on the maximum. Okay, so minimizing on the maximum. That minimization maximum is bigger than you first take the minimum and then you maximize the minimum. Right? So it's kind of like you kind of doing you kind of make the effort, like you make a big effort at the beginning, right? And then you later on you sort of like got it down, but still that effort is still a big effort. Okay, it's a big effort is a big achievement. So and that achievement is still gonna be you don't making too much effort at the beginning, and then later on you sort of you try to maximize it. Then it's gonna be then this is the minimum or the maximum is still gonna be bigger than equal to the maximum of the minimum. Right? So this is kind of like say your first choice. Okay, your first choice make a big difference. Right? This is your first choice make difference. That means your first choice. If your first choice is to maximize your target function, okay, then this is going to be split B. Even you minimize this is a later minimize it, but it still is a minimize some kind of large value because it's still a minimize of the maximum some large value. But if you starting with the minimum, you go low, then later you want even try to maximize that function, but it's still going to maximize some small value. Okay, so therefore you cannot go big. And then there's this actually serving as upper bound for this is a minimax, right? So this is max mini serve as a lower bound for this minimax. This is this clear? Everybody follow me? All right. Well, that's this is so if you with this results in mind, okay, with this results in mind, then the equivalence I wrote it on the so then this equivalence, okay, this equivalence is not that natural anymore, right? Although we just simply switch the order, you can see the value in the above actually is bigger than equal to the value in the below, right? So therefore, this equivalence is not just simply switch your order, okay? It's actually we change the problem, okay? The problem has been changed. But then the question is why do they still we can still say it's equivalent, okay? These two problems are not equivalent in general cases, okay? In general cases, they are all equivalent. They are equivalent. They have under certain constraint, okay? Under certain constraints, the constraint is going to be the problem has to be convex, and this set has to be convex. There are some constraint in there. But for our problem, okay, again, we kind of like most cases we actually satisfy the condition, okay? So therefore we just accept this as a given. Now let me just give you so like again not a rigorous proof because I find out the proof is actually not is actually hard to follow, but I do find a very nice geometric the interpretation for say to show the equivalence of these two. Okay, what I'm going to show you is it's not a strict argument, but you can give it an idea why these two minimax and max mini are equivalent in our case. Okay, in our case. Now since this is equality constraint, okay, but the argument of what I'm going to give is in the inequality constraint, okay, but the idea is the same. If you can follow or buy the argument for this for the inequality constraint, the argument for the equality constraint is also there. So let's see why this is an equality. This is minimax and max mini is enclosed. Let's see. This is let's look at this problem. Okay, we want to minimize fx, subject to some constraints gx less equal to 0. Okay, some function gx say is less equal to 0. Now, what I want to do now is suppose so the feasible region or domain in this is is x, right? So our x is our variable, right? Is our parameter. We try to work on. Now suppose this capital X, okay, is our feasible region. Okay, for any value x in this feasible region, or not even feasible region, right? For any of x, if we can project it into space, okay? And this space, we can project this as X into some this is your GX into FX. Okay. Now suppose we can project this is a we can project this is X. Suppose let's project this X into this two-dimensional space. Okay. The first dimension is simply just GX, and then the second dimension is FX. We can do that, right? For any value of X, you take in the X, no matter is a vector or is a simple is whatever, right? So you have one point. Now you have in a transformation, you can make the transformation. Then you calculate GX, calculate FX. So you project it into this two-dimensional space. Then no problem, right? Now, then this is called the primal problem. Okay, so this is called the primal problem. The primal problem is we want to minimize this FX subject to GX, which is we just said, right? This is equivalent to say this is going to be equivalent to say the minimax problem, meaning all this so we want to minimize. Let's call this okay. So this is a primal problem. I also want to talk a few concepts here. This is a primal problem. And this is we call this is as our primal feasibility condition. Okay, this is our primal feasibility because this defines the feasibility region for the primal problem, right? So this is what we call so this is a primal problem. This is a primal feasibility. And if we having this is a project to this region, okay? Now for the primal problem, what is the solution? So what if you want to find a minimize of this fx, like in this region, like if I draw in a way in this, where is which point is the minimum value? First of all, we have the what's the in this here, what's the feasible region? The feasible region should be, because this is the first dimension gx, right? I'm subject to gx less equal to 0. So therefore, only this part on the left, this will be my feasible region, right? So within this constraint, what would be the minimum point for the fx? It's just the lower point. It should be somewhere here, right? It's just a lower point, right? So for the primal problem, okay, if you have it, okay, let's just say again, the shape could be different. Just in this shape, if I draw in this way, then the problem, this is a point right here, should be our minimum point, right? This is minimum point. Minimum point, that's where this is satisfied condition. Gx is less than equal to 0, and then fx, which is going to have this minimum value right here, right here. Now, let's look at it's a dual problem. Okay? Let's look at dual problem. So the dual problem. The dual problem. What is dual problem? So dual problem will be we want to maximize y and minimize x of this is Lxy. Lxy would basically be fx plus lambda of gx, right? And the lambda in this case is bigger than 0, right? It's because we have this constraint, so we have lambda is bigger than 0, this constraint. So this is our dual problem. Dual problem, we try to maximize the immediate problem. So we want to minimize this is respect to x first, and then we maximize respect to y. When we try to minimize this is x, we consider maximize this this should be long. This that's y is 1. Okay, so this is because I'm using the y as my Lagrange modifier. Okay. So right. So in this case, we want to minimize when we try to minimize this function, we consider y as fixed. Okay, we consider y as fixed. Now for this one, what is the say suppose we given this is one. For this minimization problem, okay. So what should be the minimum value? So fx is basically our second dimension. You can say this is a, let's say let's make this to be z1, including this guy, or zq. Let's make this to be zq. This is equal to z1. So in this two-dimensional space, okay, in this two-dimensional space, fx plus g of y of gx, this is basically z2 plus y times z1 is equal to some constant c, right? So we try to minimize this is with respect to the z1 and z2, right? Because we try to minimize x. Fx and gx is defined by x. Okay, so we try to minimize. So we want to minimize. We try to minimize z1 and z2 for this function. What this minimization is going to be. This is essentially because then if equal to see this is equal to some constant c, that's basically equal to z2 equal to negative y times z1 plus c, right? This is what is c. C essentially is the intercept. Right? So if you given any particular y, okay, given a y, then what you just do is you just minimize this constant. So therefore, for any c, if for any given c, this function basically define a line, all right? Define a line with negative slope because y is bigger than 0. With a negative slope, I'm define a line across that. And then this line, there's a value of this line just basically is intercept. So for any given y, then this minimization problem where it's going to be. If you're given a slope, and what is the minimum value you want to minimize? What's the minimum for this guy? Yeah. So you think about what is the smallest intercept could be for this is a line for this is a given slope, but it still is going to be feasible. It's still going to be in this feasible region. So where it could be? You basically move this line and down here until you tangent to this make a tangent to this phase region, and then this intercept is the minimum value. Everybody follow me? Is this clear? Right? So if your y is given, then this minimization, this minimum inside, okay, this minimum is basically you're gonna move the line down and until you tangent to the phase region, then its intercept is gonna be minimum value. Okay. Now, then this is the first problem. We know this is the first problem. So first problem is given the y, we have to find the tangent line, and then find the tangent line, and then the intercept will be minimum value. So the next problem is how about if you want to maximize over 1? if you maximize over y, then what's the value is gonna be? So if you maximize over y, then you basically you're tilting the y, you change the slope, right? You change the slope. So by changing the slope, you want to making this value to the largest, right? We're still tangent to the line, so but still can making this intercept by since it's negative by making the intercept to be the largest, where that point can be. So you basically then you're tilting this line side this line tangent to this the physical region by changing, so you can go like this and then go like this, and eventually this line is going to be this point, right? You have to gradually change the slope, so therefore your intercept is going up, right? Making the slope to be smaller, and then this is the intercept to go up until it reaches to this point. And this point is exactly the same point as your primary problem. Okay, so therefore this is a dual problem. This is max mini is basically the same as minimax, right? So there are some this is again this is not a rigorous proof, okay, but this at least I think it can show you the idea to show why the minimax and max mini can be at the same solution, okay, in this particular example. This is of course this is going to involving some a little bit argument, okay. So if you kind of like I think this should be clear, okay, because the first step for the max mini, the first minimization problem, right? You basically just saying your minimized point is going to be on the tangent line, right? On the tangent line, and then your minimize the point, the value, minimized value, minimum value is going to be just the intercept. Second maximization problem is basically you change the slope, right? By change the slope, and it's still going to be tangent to the physical region, and try to making the intercept to be larger as possible, and then you're gonna find the line which is going to be exactly tangent. This is to the lower point. That's the exact same point as your primary problem, right? As your primary problem. Okay, so this is a but this is my argument here is this is ideal condition, okay? Ideal condition, okay? If you have some yield condition, okay? If you have some yield condition, which is say when you try to if your the projection from X to the two-dimensional space, the physical region is not look as nice as that one. Say for example, if it looks something like this, this will be a physical region, okay? Then the problem is not going to be the nice argument, okay? This is not going to be a nice argument. It's actually going to, you can show, because this point right here is going to be, it's always going to be your, so like the minimum point for the primary problem, but then for the minimum problem for the dual problem, it's not necessary to be the same one. There could be a gap. That gap is called duality gap. So, but we're not going to go there. Okay, so this is the argument I give you here is just mainly try to show you there are scenarios. This is a minimax problem, which is actually equivalent to this max mini problem. Okay, so the equivalent problem. Okay, so this is hopefully this can give you some idea to say when you go back to this slide. Okay, now you go back to this slide. I think this slide now is not that so like a weak anymore, right? So basically I showed you this Lagrangian problem is equivalent to in our case, okay, can be written as this a max mini problem, okay, max mini problem. Then once we have this is minimax and max mini problem, what are we going to do is is the goal is we try to set up for this is a problem for this dual so-called dual ascent the algorithm, right? So the dual ascent algorithm is okay, let me. So I want to get in this concept of this is a primary problem and a primary feasibility condition. I want to having this is a two. Okay. So for this problem to hold, okay? For this is a problem to hold. We want to maximize. I want to minimize. This is this function right here. Now, in order for this minimization to hold, okay, we want to having this maximization done first. Okay, we want to have this maximization done first. So therefore, if you want to have this maximization done first, then the gradient of this is L x y respect to y, because this is maximization of gradient respect to y, right? This has set to equal to 0. It has to be equal to 0, which is in this Lagrangian, if it has gradient respect to y, which is ax minus b, right? X minus b. So this is equivalent to say ax minus b equal to 0. So this condition, okay, this condition is the so-called primal. So this is our primal problem. This is our dual problem. Then this condition right here, this is called a primal feasibility condition. All right, because in order for we do this minimization, first we have to maximize it first, right? Or to maximize it. In order for this maximization to achieve, then we have to set in this is this gradient respect to y equal to 0, and then ax minus b equal to 0. So, but this is serving as a condition for the minimization, right? So that's this is a so that's called the primal feasibility condition. Now, in order for the dual problem to work, right? You want to maximize y, then we have to making this, we have to minimize this is the inside first, right? Or to minimize it first. So minimize it first, then then this is we can define correspondingly. If we take the gradient of the x of Lxy, this equal to 0 has equal to 0. And this condition, okay, this condition basically is equivalent to the gradient of fx plus a transpose y equal to 0. This condition is called the dual feasibility condition. Right? This is dual feasibility condition. So this is the dual feasibility or the primal feasibility. Okay, this two thing. This is so basically the primal feasibility condition is the same as the origin constraint, right? The same as the origin constraint. The dual feasibility condition is just the Lagrangian taking gradient with respect to x and set it equal to 0. That's a dual feasibility. So you're gonna see this two concept like in the next few slides. But here I just want to have a concept the first. Now with this setup, so for the ones on the for those on Zoom, basically I'm just saying is for the primary problem, right? So in order for the minimization for the outer minimization to work, then the inside you have to do this maximization first, right? So if you for this maximization to hold, basically that means the gradient with respect to y equal to 0. So that's equivalent to primal feasibility. For the dual problem, in order for this to do the maximization outer on the second step, then we need to have the minimization first to work. In order for that minimization to work, then we need to have a gradient of the Lagrangian with respect to x equal to 0. So therefore, this is our dual feasibility condition. Okay, so that's this is two concept. Yeah, I forgot to stop sharing, show the whiteboard. All right, so any question on the primal feasibility and the dual feasibility? Is this clear? Yeah, this is just the corresponding to the two problem. All right, so then we can come back to this so-called dual ascent problem. Dual ascent problem. Then what just basic thing is we want to iteratively, right? We want to iteratively to update this x and y by because this is we can one is a minimization. If we know y, then we can just minimize it, become a private problem, right? If we know x, then we can just maximize y for the dual problem because they are the same, right? They're the same. So therefore, in this is a dual ascent algorithm. What we do here is we want to if you're given a y, if y is known, like in the iterative the algorithm, right? So you have in the x y value from previous step. So if you're given the y, then you can just basically minimize the Lagrangian with given y. You minimize this with respect to x, you get an x cubed plus 1, right? Then for the so this is a primer. This is a primer problem, right? So then in the second step, we given the x, then we can update the y, okay? By maximize this is the dual problem, dual function. But so this is also called dual update. The reason we cannot maximize because the maximization, just directly for this maximization, is actually infinity, right? So what are we going to do in this step? Instead, we update y in the direction of its gradient, okay, a little bit, okay, a little bit. So to making this to making this this value to be larger, okay. So therefore, we can iterate between these two steps and make it work. This is actually not a bad algorithm, okay. It works, but it having it with a lot of strong assumptions, okay. You have to making like convex. You have in the convex set and a lot of convex the condition for it to work. Then the way to solve it, okay, way to solve it is actually going to be this is a so-called method or multiplier. The way to make it work is to make it less like the numerical step like a little bit more stable is by changing the problem by adding this is the quadratic term into Lagrangian function. Okay, so this fx plus y transpose x minus b, this is the original Lagrangian, right? By plus some, this is another quadratic term into here using the some rho minus 2 times ax minus b, the square of L2 norm. This is actually then this problem is essentially is the same problem as one above. Okay. Now, why this is the same? Because this minimize fx subject to x minus b is equivalent to say minimize fx plus rho over 2 of ax minus b subject to ax minus b equal to 0. These two are the same, right? Because your feasible region is what? Your feasible region. Oh, okay, for those who are on Zoom, I'm basically saying the original minimize fx subject to ax minus b is equivalent to say minimize fx plus rho over 2x minus b, the square of L2 norm subject to ax minus b, right? They're the same. The reason is either if for the minimized whole, you have to be feasible. When ax minus b equal to 0, then this second term actually vanishes, right? It's actually vanished. So therefore, they are, and then the Lagrangian for the second term basically is a massive multiplier. Okay, it's a massive multiplier. If we come back to the slides, this Lagrangian essentially is this function right here. This essentially is a function for our equivalent problem, right? So why do we want to add in this is another term into minimization? This is because this can making our problem like a little bit more stable, okay? A little more stable. If we want to maximize this function, okay, to do this is a maximize function above, if the dual ascent still works, okay, dual ascent still works. So basically, what we do is we first you have x y, if we're given yk, then we update the x to this problem, right? Then once we know the x, we update yk. So that's the problem is the same. The only thing is in the first step. Okay, the only thing in the first step, you have the L2 term right here, which can make it more stable. Okay, if you are a little bit familiar with in the ridge regression, you know, in the ridge regression, you add in the second penalty to the L2 norm penalty into there. You can make in the original motivation is actually making the algorithm to be more stable. Okay, this is the same idea. So this is a method. This is a method. The multiplier. Okay, this is where the method multiplier come in, or method moments. This is because we're adding this is a L2 term into there. Now let's go back a little bit. Okay, let's go back a little bit. Let's suppose. Okay, let's suppose your function f(x) is actually separable. By separable means your original function f(x), okay, your variable x can be written as x1, x2 up to xn, right? You can have like n variable, and this variable can be separated into different subfunctions. Okay, so this f1 x1, it will be the function just contain x1, no other variable. Okay. Then fn xn only contain xn. It doesn't have the other variables. Okay, so this we call if fx can be written this way, then we call this the fx is separable. Now, what kind of functions are separable? I mean, if fx say just two values equal to x1 squared plus x2 squared. Is it separable? It is separable, right? So this is because now you can basically write in as this will be your f1, x1. This is going to be your f2, x2. They can be written into separate function, right? Now, if fx equal to x1 squared plus x2 squared plus x1 times x2. Is this separable? It's not separable, right? Or you can say this is to be e to the power of x1 plus x2, fx equal to this guy. This is also this is also not separable, right? Because this is essentially this is equal to e of x1 times e of x2, which you cannot put into the summation, right? But it's not separable. So separable function is actually a very small fraction of the problem is separable, okay? It's separable. But when this happens, okay? But when this happens, which is going to be this separable function, we can, in our case, we're gonna make, okay, we're gonna make our target function separable in the big data analysis. But now, just bear with me for now. Is let's say, although it's a rare scenario, but we can tailor our problem. Okay, we can make our problem to be a separable. If this is a f function is a separable, okay, then the Lagrangian function is also separable. Okay, Lagrangian function is also separable. By basically is we can separate our Lagrangian function into this is into this is Lxy equal to Ly x1y up to n x ny minus y transpose b, right? So this is Li xi, y is just equal to this is fi x ax plus y transpose ax xi. Because our linear constraint, because what is the constraint in this case? Our constraint is ax minus b equal to 0. This is a linear constraint, right? This is a linear constraint. So if we can write in this is a it'd be like a1, a2 up to a actually the should be writing this. Okay. A1, a2 up to like an, you prime this is x1 up to xn. Then this is ax minus b is minus b1 up to like a bn, right? So this actually can be written as equal to going to be summation j from 1 to n of ai times xi minus bi equal to 0, right? So this is ax minus b by because this is a linear constraint by default is separable, okay? So the constraint is separable. Therefore, your Lagrangian function, if fx is separable, your Lagrangian function this is going to be equal to summation I from j from 1 to n of fj of xj then plus y transpose times summation of a of xi and minus y transpose b equal to 0. Let's not separate b, okay? So let's just separate a. So it's minus b minus b is open, right? If you can do that, then this is equal to summation j from 1 to n of fj of xj plus y transpose a x j. This will be the thing minus y transpose b equal to 0. Now this thing right here, okay, this thing right here is your Lj of xj1, right? Because it contains the Lagrangian. So if your function fx is separable, okay, if separable is separable, then you can basically, when you minimize your Lagrangian function, you given yk in remember in there, then we can minimize this sub function separate, because this is xi they have no overlap, okay, they have no overlap. So therefore you minimize this Lj xj has nothing to do with other xj, right? So therefore you can separable. Then in the dual ascent, okay, in the dual ascent, we can, so in the dual ascent, basically in the dual ascent, what we do is we minimize. So in that step, we minimize of x respect to the L x y k. Remember, right? So this is we want to minimize this. So minimize this is equivalent to say we want to. This is equivalent to say we minimize Lj of xj with yk, or j up to, or j is 1 up to n, okay? Right. So then this is xj is separable. We just assume this is based on assumption, right? Based on assumption, xj, your fj is your fx is separable, can be separated in the summation, or this is a subfunction. Then by the definition by the definition, because ax minus b, this is a linear constraint, is also separable. So therefore, in the dual ascent, want to minimize this is the Lx yk respect to x is going to be equivalent to say we want to minimize each of xj for j from 1 to n, right? We want to minimize the separate. This create if your function f is separable, okay? Now you can say you can basically then that's parallelization come from. You can parallelize your algorithm, okay? So you don't need to have to wait until because this is essentially since it can be individually maximized. So that's where the parallelization or the speed up can come. Yeah.
Right. Sigma equal to 1, j equal
Yeah.
Yeah.
The y transpose time this time. So this is the
minus y trans sigma j equal to 1 to n, bj equal to 2. Because in the previous case, when we wrote ax minus b equal to 0, that's how we wrote b as a matrix, which runs from b1 to bn.
no. This is a y is a Lagrangian. So this is b. So this should be y transpose b. There's no. Your original is this y transpose ax minus b, right?
No. Previously when you wrote a sigma j equal to 1 to n, aj xj minus bj equal to 0, right?
Oh, yeah. Well, that's the b. You don't need to. Yeah, that b is actually that's a typo because b is same. You cannot separate into bj. So that's yeah. So we still need this. We still need this one term. Yeah. So that's I know I separated bj, right? So that bj is basically so your ax if you do that, then the yi has to be also to be separate, right? Your y has to be separate. So here is a1, a2 up to n, right? So your x is x1 up to xn. X is n by 1 vector. Your a here is a1 is gonna be like n1 by n. So it's n by n1. It's actually so it has to be the what did I make it to be the
Because after minus and then a matrix b1, b2, and so on to bn equal to 0.
yes. So what do we want to do here? So A matrix is a P by n vector matrix, right? It's a P by n matrix. So we only having this is the n, this is n1. So x1 is n1 is vector. So this n1 by 1. This is going to be equal to b1. It's going to be also this is n1 by 1. So we want to separate it out to be in such a way. This one is n1 by 1, which is this guy right here. Is so this is A1.
Final matrix p by 1.
Final one is a P by 1 for the AX for the A1 times x1.
A1
Yeah.
By 1 time. So ideally that should run from 1 to n. 1 to p.
Yeah. Let me think a little bit. I think it's a little bit confused. So we want to separate this system. So it has to be A2 up to AN. It has to be this way, right? Because in this way, then this part is gonna be P by N1 matrix. So this is P by N1 times X1 is still gonna be a P by 1 matrix, right? So you separate it, but this B is also constrained. This is B, although it's B is not separable. So I actually have a typo in the previous slide. B you cannot be separated. So your A1 is a P by N1 matrix. This is N1 by 1. So then it's gonna be a P1 bind. So basically separate B1, if you write it that way, B1 is sort of like breaking into columns. So B is not separable.
So in that formula up there, sigma j equal to one f j x j, that whole line.
Yeah.
We cannot write sigma j equal to 1 to p equal to 0.
No, you cannot write in that. You cannot write in that. Yeah.
Why
So-
can't I suppose that p matrix single column?
Yeah. So this whole thing is equal to that. So yeah. So I then forgot about what I write a BI. That's a typo. That doesn't work. Okay. Okay. So let's stop here. So we're gonna continue in the next class. So then the next thing we need to fix is how you combine a dual decomposition and this is a mass multiplier together. Okay. So this is what we're gonna do next class.